So today I'll be talking about something that I've been working on since the last couple of months uh, on optimal transport on the Lee group of roto-translations. And this is joint work with some very nice colleagues. So there is Dan Born and Kais Ballard, who are PhD students in our group, and Olga Mula and Remco Deutz, who are associate professors at our cluster, which is called Center for Analysis, Scientific Computing and Applications at TUE. So broadly, the outline of my talk is the following. So I'll spend some time on the topic of image processing on SE2 and what do I mean by that. Then I'll say some very basic things of definitions of optimal transport on geometric domains. Then I'll sort of get to it and sort of have combine both of these things and talk about doing optimal transport on SE2 with a focus on discussing symmetries on what does it mean to be invariant and equivariant, right? And also the extension of the entropic regularization problem to homogeneous spaces. And then I'll show some applications, specifically barycentric interpolation of images, orientation fields, an example of a Wasserstein gradient flow, and then I'll finish with some future directions, right? And so let me get to it right away. So basically, what do I mean by SE2, right? So we think of images as functions of positions, right? And I'm going to talk about lifting images to a space of positions and orientation. So we gain a dimension, and such functions are called orientation scores. And then we do our processing in this lifted space. And then we reconstruct to get your output image back, right? So this is basically the broad template of almost everything that I'll be talking about today. And most things we like to do with images, we now would like to sort of do it in this lifted space. So for example, when we talk of applications, so for example, you may want to do, say, tracking. So let's say you have an image of, say, a vascular tree-like structure shown here. And then given a seed at point A and target at point B, you want to find out sort of like the shortest path that goes from A to B, right? And so there are innumerable ways to do this. And just as a general remark, I'd like to say that you can sort of also do this by lifting the image into the space of positions and orientations and do the tracking there, and then project that back onto your image domain. And the advantage of doing this is that we can sort of put certain nice constraints on our tracking in this lifted space. So for example, we can say that we don't want to sort of abruptly move to the side as we track from the source to the target. So for example, another example is, say, diffusion, and one may want to do, for example, what is called crossing preserving diffusion. So your image contains a lot of structures which have like crossings and bifurcations, and you want to apply some sort of denoising or diffusion, right? And the desire is to preserve these sort of crossings and bifurcations. And again, you could do this generally in R2, but you could also do it very conveniently in by lifting it into the space of positions and orientations and then projecting it back. More recently, the focus has been on developing deep learning architectures on this space. And so I think a lot of us would be quite familiar with convolutional neural networks, right? And it is sort of known now that these are equivariant to the translation group, right? So I have some kernel K, which I sort of shift around my domain and then take its sort of inner product with my function. And one can show that this is equivariant to translations. And what do I mean by equivariant? I can do a convolution and then sort of translate, or I can translate first and then do the convolution. I get the same thing. And so this idea can sort of be generalized and written it in a general setup for general kind of transformations to linear group convolutions. And so specifically when we talk about the roto-translation group SE2, you can write down SE2 linear group convolution by defining a kernel onto this lifted domain, applying what I call a left action, or doing sort of like shifting it to the corresponding location by roto-translating that kernel there and then taking an inner product. And this is equivariant to roto-translations. And you can take even a step further and define what are called morphological convolutions. So the idea is, again, that you have some kernel K. And then instead of like taking an inner product, you sort of take the maximum or minimum in a ball that's sort of defined by that kernel K. And something that was an output of our group is what is called as a PDE-G CNN, which is a neural network that comprises of PDE layers. And two important PDEs that are used in this layer is erosion and dilation. And it's nice to see that the solutions to these PDEs are basically morphological convolutions that I have shown over here, right, with some specific kernels. Right, and so what I'll be talking about is, amongst various applications that I've shown here, how to do sort of optimal transport. And by that I mean how to define a Wasserstein distance, how to compute a barycenter, gradient flow, etc. In this lifted space with all its properties and metrics that one can sort of choose in this domain. So by the way, I just like to remark that feel free to interrupt me anytime. If anything's unclear, I would be glad to sort of answer about it. So let me begin by very basic preliminaries of the Lie group SE2. Right, so SE2 is basically comprised of the coupled space of positions and orientations, and one can define sort of like a group product, which one can derive from a roto-translation, right? So if you have a group element G and a group element G prime, sure I have my pointer kind of works, but so if G is given by the position X and the rotation R theta, and G prime by X prime and R theta prime, then we define the group product to be a new position and orientation, which is R theta X prime plus X, and the rotation to be R of theta plus theta prime. And one can define the inverse element as minus R theta inverse X and minus theta. And I just like to mention that SE2 acts both on R2, which is just the space of positions, as well as M2, which I am denoting. M2 is just a term I'm going to call the space of positions and orientations. And both of them are homogeneous spaces, but M2 is a principal homogeneous space. And what do I mean by that is that given any two positions and orientations, there is sort of like a unique group element that takes you from one position and orientation to the other. Okay. And so the Lie group is, of course, a smooth manifold. So you can define a tangent space or a Lie algebra. And one can work out that you can sort of choose a basis for your tangent space. And that's given by these three sort of operators, A1, A2, and A3, which are basically achieved by sort of left translating the standard frame at the origin to wherever, whichever group location that you're sort of wanting to evaluate it at. And so given a tangent space, given a basis for the tangent space, you can define a metric, right? And since we have chosen a left invariant basis, you can define a left invariant metric tensor, which is a 3x3 matrix, right? And so generally we, for the purposes of this presentation, most of the metrics that I will be choosing are diagonal. But the important thing is that I'm going to call something called as the spatial anisotropy of this metric, which is the ratio of basically the first two elements, whichever is larger, right? So when the anisotropy is 1, you have your sort of distance that looks like a sphere. And as you sort of increase your spatial anisotropy, you can, this sphere sort of like deforms into a Riemannian ball, right? And the important, I just like to, before going ahead in the slides, I'd like to make a comment that the interesting things happen when your anisotropy is kind of like high, right? Like, so it's interesting to do stuff on this lifted space of position or orientations with high spatial anisotropies. And since you're choosing a left invariant basis, the whole thing is indeed left invariant. Okay. And so how do we work with images? So we lift, so we say we lift an image into the space of position and orientation by basically convolving with some filter which is parameterized by an angle theta, right? So generally one can choose any filter, right? And you can sort of, which is, since it's parameterized by orientation, you can sort of convolve your image and record its response for each of these orientations, and you get a stack of responses, which is your orientation score. And the nice thing is that if you choose filters of this type, which are called cake wavelets, then you can sort of reconstruct your image quite accurately by just integrating along the theta direction, right? So your lifting is basically convolving with different filters, which is parameterized by theta, and then if you want to reconstruct, you just add it up along the theta direction. And so importantly, in terms of how the group acts on both the image and its orientation score, so if you roto-translate your image, right? So I say that I apply a left action UG on F, right? So that can sort of roto-translate. Its corresponding action in the lifted space is a shift twist, which is, so your angles kind of like increase, right? They go on top, and then I call the left action in this lifted space as LG. And because we choose to lift in this specific way, these two things commute, right? So I can sort of roto-translate my image and then lift, or I could lift first and then apply a shift twist, and in principle, like they are basically going to give you the same result. So,
sorry.
Yeah.
So you start from an image,
Mm-hmm.
from R to R, and so at the end you get something which is, when you do the lifting, you get what?
You get something which is M2 to R. So M2 is the space of positions and orientations. So it's a three-dimensional space.
2R. Yes.
2R. Right.
And just to be clear here, the way you display it, you discretize the space of orientations, but do you use some kind of steerable tricks to make sure that actually you're not really losing anything related to angles? Because here, as we see it, we assume that you discretize with like 32 angles, and so you
Right. So as a general comment, that's what it is. Like I discretize with like 32 angles, and we ensure that in all our operations, like the circularity is sort of preserved and all that. But that's basically it. Yeah. Okay. And so why do all this? So I'll sort of describe quickly sort of three advantages of doing sort of image processing in this way. So given an image, you lift into this orientation score, you do some processing. So now this could be denoising, it could be a neural network, it could be tracking, right? And then you take a processed orientation score and then sort of project it back, preferably by adding up along the theta direction to get your image back. And let's say my process is sort of denoted by this operator phi over here. Then the idea is that if that operator commutes with the left action, then the whole process end to end is equivariant, right? So this is basically something that I claim is desirable. So you lift, you do your processing in for whatever application you want, you project, but you must ensure that your operators should sort of commute with the left action, and then you are guaranteed that you have achieved full roto-translation equivariance from end to end. And so what are such examples of phi? So like I mentioned earlier, a linear group convolution, right, is probably sort of commutes with this left action. And something simpler like say doing pointwise operations or nonlinearities also will do, right? So, and this is basically the fulcrum of sort of designing equivariant or roto-translation equivariant neural networks, since now you have like a pipeline to do everything end to end. As it turns out, sort of this is also the basic ingredients, as I will describe earlier, to also do entropic optimal transport, right? Like so. All right. The second advantage is this property of contour propagation. So I'm going to show you a video here, which was sort of nicely compiled by Kais. So this is a Riemannian ball that I'd shown earlier, which has a very high spatial anisotropy. And these black lines are basically geodesics, right, that pass through the origin here. And now I'm going to sort of place this ball at each of, so I have an image here which contains a lot of local line structures or local orientations. And I'm going to place this ball at each of these line structures and do some kind of propagation. And we hope to see some pattern that comes out of that. So you have your image containing these local orientations, and then you lift them corresponding to the local orientation, right? And then I sort of place this ball at each of these locations and then sort of do some kind of propagation. And in doing so, what happens is basically you have some kind of contour contour propagation or contour perception that sort of comes out, right? And so this is also one of the nice properties of working with sort of anisotropic metrics in this lifted space. And finally, something that probably is a little bit obvious. So if since you're lifting it into this space of like positions and orientations, it's easy to sort of disentangle crossings and bifurcations, right? Like so, if you want to do tracking, for example, it's easy to impose that you essentially want to have only a forward movement. So something that I did not mention earlier is that these metrics have an interpretation, which is that so A1, for example, or choosing a high value of W1 essentially means that you're penalizing forward movement. Like so, if you're, for example, thinking of doing tracking, then a high W1 would mean that it costs a lot to move forward wherever you are. A high W2 is the cost for moving sideways, and W3 is the cost for changing your orientation. Right? So it's got this interpretation.
What is moving forward?
By moving forward, I mean that so when you are at some location in your lifted space, right? And let's say at that location, if you want to do some diffusion, right? It has an interpretation of forward means that you move along A1 direction, and A1 is given by this operator over here. So you move locally along the orientation that exists at that location. So for example, in the case of this video here, forward basically means if you are over here, then you sort of move ahead, connecting to the orientation of the next line structure over there. I don't know if that makes it a little bit clear.
To be super clear, when you say forward, it's forward and backward.
That's correct. 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 Right. So W1 will tell you So W1 is just the penalty for moving forward. W2 is penalty for moving sideways. So if you do say a diffusion using these parameters, then maybe it will become clear when I actually show you examples of such diffusions. Okay. All right. So given this sort of introduction to SE2, I'd like to say very basic things about optimal transport. So generally, it gives you a set of tools for working with probability distributions, right? So one would like to compare, interpolate, propagate, etc. And so it's interesting to sort of apply these tools in geometric domains, like for example, the Lie group of interest here. And so at the core of it, we can define the Wasserstein distance, right? So given a distribution mu and nu and some ground cost d, right? So you can compute sort of the optimal plan that takes sort of the distribution mu to nu, sort of minimizing this particular cost. And this ground distance is typically chosen as the geodesic distance. We can discretize this and sort of ask for sort of a matrix T, right? So which minimizes mass times distance, such that if you sort of add up along, say, each dimension, you get each of your sort of marginal distributions, right? Okay. And generally speaking, so this would require all possible distances, right? And one has to implement a linear program, which typically contains a quadratic number of unknowns. And so amongst the many applications, one that is nice in terms of working with shapes is you can do sort of meaningful interpolation, right? And given the ground, typically the Euclidean costs say in R2 and R3, you can get sort of like meaningful interpolation of shapes in this domain. And so you can also use the Wasserstein distance to do gradient flows, right? So if you, it's well known now that if you sort of apply this iterative step with a specific choice of f, depending on which application you're doing, then this sort of converges to the to a particular PDE, right? And so a lot of this again is just very basic stuff for so there's nothing new I'm saying here. And what I'm getting to is that we would like to do all these applications for this lifted space of positions and orientations. And so that's what we try to do. So you basically define your distance as the left invariant distance. and you choose your left invariant R measure, and you integrate on your Lie group, right? And it turns out that if you do so, then the Wasserstein distance is invariant, which means that if I have two distributions mu and u and I roto-translate them, right, or shift twist them in this lifted space, then the Wasserstein distance between them is invariant to group action on both its arguments. The Wasserstein barycenters become equivariant, which means that if I apply the group action on all my input arguments, right, then the corresponding barycenter also transforms accordingly. And a similar result also holds for gradient flows. And then we sort of go ahead and apply entropic regularization to it, which is you sort of add an additional term of entropic smoothing, right? And again, so this is basic, like nothing new here. This is all calculation that's sort of been well known. It's just that it's been applied now on a homogeneous space. And you essentially get the Sinkhorn steps, which sort of iterates between computing these terms V and W. And if you choose a left invariant distance, then this essentially boils down to a group convolution, right? So one can work that out and show that this is essentially nicely extendable to Lie groups as well. Right, and so what we did was basically sort of used much of the algorithmic machinery that's already available and just applied it to the Lie group SE2, right? And so if you look at the ingredients for doing that, so Lie group convolution is something that's now quite widely available for various kinds of Lie groups, especially since they are used in various geometric deep learning architectures. You also would require a Gibbs kernel, which is given by e to the power of minus the actual geodesic distance on your manifold. And something that's well known is that instead of computing the Gibbs kernel or computing the geodesic distance, one can sort of use heat diffusion on manifolds. So I'd like to make a point here that for anisotropic metrics, the geodesic distance in SE2 does not have a closed form, right? So one has to resort to some iconal or numerical implementation to get it. But what we did try was to sort of approximate that using logarithmic coordinates for SE2. So generally, the sort of high-level idea for the approximation is the following. If you basically have like two sort of position and orientations which are sort of close by, right? Then you can approximate geodesics with exponential curves. So exponential curve is basically the roto-translation that takes you from one position orientation to the other. You can approximate geodesic distance as the length of this exponential curve using a left invariant metric, right? So ideally, if you were to compute geodesic distance, you would have to find that curve which minimizes the length functional, but we approximate, we choose a specific curve and approximate its length as the using this length of this curve using the left invariant metric. And we further make some modifications for SE2 using half angle coordinates. So
why is this an approximation? I understand because in fact you compute the exponential for the Riemannian exponential or
the Lie group exponential.
Oh, okay.
The Lie group exponential. Yeah.
This is why you have an approximation.
Right. And so, so this is basically how it works out. So you can work out how the logarithmic coordinates look like. So you have your left invariant basis A1, A2, A3. You can sort of locally get coordinates C1, C2, and C3. And rho C is basically its local distance approximation from the identity element, of course, for some metric parameters W1, W2, and W3. And we go a little bit further. So we sort of drop this sinc term that exists, and we work with what are called half angle approximations. And we can show that basically for sort of reasonable spatial anisotropies eta, our approximation is kind of decent. And we always work with this logarithmic approximation rho b, which is basically given by this formula over here. And we can also see that sort of by numerically computing it. So if you have your exact distance, we compute its analytic half angle approximation. And we see that roughly speaking, it's sort of like a good approximation to be used in our application. And the nice thing is that sort of we extend this result of bounding your approximation to also the Wasserstein distance. So it turns out that you can also say that the Wasserstein distance computed using these approximations is also bounded by the amount of anisotropy that's been used. Okay, so one of the first experiments that we tried to do was to just work in terms of sort of Lagrangian interpolation. So you just sort of take some curve and then look at its normal, and then you have a bunch of sort of positions and orientations. And then you want to sort of evolve this, right, with the left invariant metric that we have chosen. And generally speaking, this is just to highlight to you that if you choose, for example, an anisotropic metric, it's got this forward kind of like movement to it. And obviously working with positions and orientations is better than not working with orientations at all, right? And so in the case of R2, you do have some sort of collapse that does happen, but when working with M2, both with isotropic and anisotropic metrics, you get somewhat of a reasonable evolution. In general, this is not very stable for doing shape matching, so I do not recommend using this generally speaking, and I think you would need more information like descriptors, local descriptors to get you accurate matches. And so this brings me, so it's sort of a slight digression, but sort of one of my earlier...
So, could you explain what we see on the first three?
So
On the bottom line?
This one here. So what you see here is I've taken an MNIST3 and sort of extracted its contour and then sort of discretized it. And at each location, you have a position and an orientation, right? Then I say I basically do matching between these two positions and orientations using optimal transport. I don't know if that...
The orientation there, okay, normal orientation.
Normal orientation pointing outside, pointing outward. And then I basically say, okay, the distance between this point and this point is the left invariant metric that I talked about, right? And I do it for all points and then sort of use that as my...
You compute piecewise geodesic between each couple of points?
Each couple of points, that's right, that's right.
Why?
That distance is given by this formula here. Yeah.
Okay, but to be clear, what you say with the actual distance is what you have on the right. But you know what's surprising is that the left one is really, really terrible. Like there's not even a matching. So
right, because it is not using orientations at all. It's only R2 distance.
Yes, but you know, if you do optimal transport just with R2 distance, you would expect shearings, but at least between time 0 and time 1, you should observe the two.
Yes.
The two shapes. You know? But here, it seems to stop in the middle of nowhere.
I see. I must say that all this is so. When I say that this is not good for shape matching, all this depends on how aligned your two initial point clouds are already. So if you're, so these two, I mean, you see a collapse here because probably like...
it did not really converge or equal stability.
I would think it's converged, but my interpret...
Or maybe you're using entropy and the blur is large.
I see.
This is what's happening.
I see. Yeah. I mean, I don't want to say that this is like a successful application. This is just to highlight that, you can use sort of these metrics for...
You compared this approach with matching with varifolds?
With varifolds, that is interesting. I don't discuss that at all over here. Yeah. But generally in varifolds, you have this sort of also positions and orientations, and they are decoupled. And a lot of my emphasis is on metrics that are not decoupled. Like so, it's left invariant, but you can't sort of separate the positions and orientations. That's something that I do.
Yeah, but on this example, you are doing the optimal transport on the distribution of position and orientation.
Yes.
Okay.
Yes.
So it's not point to point.
It is point to point. I just assume that it's uniform on both the trees, and then do.
So, but you don't need to have any point correspondence in the two point cloud. In this.
You have to say, so it's matching, distributions, it's matching of measures. It's just that I think because people here they are very used to a specific type of cost function on the space of orientations, points and rotation. And here it's like you're proposing a more invariant or a different cost function.
No, I mean, you have the first three. It's a distribution on M2,
right?
and the second is the distribution M2, and you do the optimal transport between the distribution.
I would say so, yes. Except that the distribution is uniform over all the points that I've chosen here.
Yeah, exactly.
Yeah. And the output of the optimal transport is a matching. Which also, again, there is some tricks I did here to sort of, because Sinkhorn ideally doesn't give you a point-to-point matching.
Yes.
So, yeah, I mean,
Yes.
yeah.
Okay.
Yeah. So, with regards to sort of matching with particles, I will digress a little bit and talk a little bit of something that I did a couple of years ago, which was to use it in the context of 3D shape matching, specifically in the context of what are called functional maps. So, sort of without not going too much into detail, the general idea is that given two shapes, right, you can sort of compute the Laplace-Beltrami basis on each of these meshes, and then sort of estimate a functional maps that sort of aligns these bases between these two shapes, right? And what we did was, once you get the functional map, you think of these two shapes as just point clouds in high dimensional space with spectral coordinates, and do optimal transport in this sort of in the space. And in this particular project, we were able to see some. So this was basically the pipeline. So you have your sort of spectral coordinates for shape X and shape Y. You populate your sort of kernel matrix given by sort of ideally all possible pairwise distances. But in this case, we make an assumption of choosing only k nearest neighbors in order to populate this matrix. And then you do Sinkhorn iterations on this, and you get sort of like a smooth entropic transport plan, which we then sort of hard discretize and choose the maximum to get a choice of final correspondences. And in this particular setting, we were able to sort of see that amongst many things, so it sort of compared well. So there are two other things that one can do. One can actually solve a linear assignment problem at one end, or do nearest neighbor, which is quite popular in the functional map shape matching community. We sort of use Sinkhorn as sort of a replacement for most algorithms that use the nearest neighbor or the auction. And we were able to see that we get a fair trade-off between being fast, being bijective. And by bijective, I mean, given a point on the source shape, if you sort of map it to the target, and then given that point, and if you map it back, ideally you should reach the same point, right? But depending on what sort of method you use, you probably will not. But in the case of like using a Sinkhorn filter in this particular way, you sort of get a more bijective correspondence, which is also fairly accurate for the kind of data sets we used in this setting. So this was just a quick digression. So this was my first interaction with using Sinkhorn. Okay, so back to our setting here. So we now have the ingredients for doing optimal transport. We have an approximation to our Gibbs kernel, and we know how to do a Lie group convolution. One of the first things that we did was to sort of just as a sanity check, see if it agrees with what the theory says about, say, sub-Riemannian geodesics. So in this example, what are you seeing? You have a source which is at the top left and a target at the bottom right. The orientation in this case is both are pointing at 0 degrees, right? So you have your point here, which is pointing towards, let's say, the right, and you want to interpolate that between point in the bottom right, which is also pointing at, which also has 0 degrees, right? And you want to transport with a metric which is highly anisotropic, which means that you're only, the penalty for moving sideways is extremely high, and you're only allowed to move sort of forward, right? And from the red curve is what sort of you actually compute these sub-Riemannian geodesics, and one sees that they are S curves, right? So you can think of a car that starts at your seed and which is only allowed to move forward, right? And so the trajectory it takes is sort of like an S, which goes from the top left to the bottom right. And it's nice to see that when we applied sort of interpolation using the technique here, it agrees with this trajectory, right? Like, so you have your point mass that goes pretty much along your sub-Riemannian geodesic. So this is just a sanity check that what we see from theory and what we sort of implemented using these approximations is okay. Right?
And to be clear, because you kind of presented two ways of computing your distance. First was like heat diffusion, and the second was with an approximation of the distance.
Right.
Here it seems that the second approach is way better.
Right.
So in practice, you tend to just always pick the second approximation, or sometimes you still use a heat diffusion.
My instinct is to tell you that we always choose the second one, right? But I have to honestly declare that the way we implemented heat diffusion, so even there are many ways to do that, right? So first thing, the heat kernel for SE2 does not have a closed form, right? So that's the advantage of working with the Gibbs. So you can just convolve it once. What you see in the first row here is basically discretizing basically the Laplacian. I'm doing a forward Euler step as your heat diffusion because you just convolve. You convolve with your discretized Laplacian. One can argue I can get an even better discretized diffusion and probably get sort of a more accurate. So this is like within the realm of a fair compute trade-off. We see that indeed our approximation was fine if you sort of just, yeah.
How long does the time need to be?
Sorry?
How long does the time need to be?
For the diffusion? I find it hard to tell you a number.
Is it short?
Roughly speaking, both these simulations take the same time.
No, I mean in terms of like how many time steps do you need? Do you need to run the diffusion for many time steps?
Yeah, for sure, yeah. At least in this case, we did. I mean, it's obviously better if it's sort of much smaller, but yeah, we did choose a couple of iterations of the time. Yeah.
And why for this reason, so you said the second one is better? Is it obvious? I don't see why that's.
So in this particular case, it sort of adheres to the actual geodesic more accurately than the first row.
Like it looks like an S without.
Yes, that's the problem, but I don't understand the last one. I just see the geodesics.
So this is basically, it's like sort of the time steps at each, the value at these time steps. The last one is just an integration of all of these time steps. So you just add everything up.
Okay.
And then you tend to see a trajectory.
Okay. Because the red curve is not part of the computation. It's just the theoretical.
That's correct. It's the same red curve up and down. Right. Okay. And then we applied it to, for example, say MNIST, right? So computing barycenters of digits. Please.
There is a to turn. W3 is high. On the side would be a straight line. Oh, yeah. If W3 was very high,
if this one, yeah. So so over here, W1 is smaller than W2. So which means that it's much cheaper to move forward than to move sideways. And W3 is the cost of turning.
1 million. It would be some kind of straight line, and it would just on the side.
So if you're not allowed to turn at all, yeah.
Yeah, presumably it's just like a car and you drift on the snow.
Yeah, I think so. I'll have to think about it. Yeah. I do have another similar example. Maybe that might also help. Okay. And so we tried it for digits. So you have your simple barycenter, which is just adding up all your digits in your data set. You compute the Wasserstein barycenter in R2, and then you do the Wasserstein barycenter in SE2, and generally you see sort of like meaningful interpolations with in the homogeneous space of SE2. Then we sort of thought of using a more interesting data set, which comprises of a lot of doodles, and which are basically people online can go and make sort of like a doodle for each class, say a star or an umbrella or whatever. And even over here, we see that if you compute, sort of compare between them, it's sort of meaningful in terms of using it in SE2 in comparison to doing with R2 or, for example, the simple barycenter. And yeah, so this is just to sort of, just compare between. It's the same example where when you do it in SE2, you have these contour concentrating behavior due to the anisotropy that we use. Then we tried of interpolating between orientation fields, which are basically positions and orientations, like sort of the example earlier. And so you lift by literally just taking, given you just put sort of like an indicator, like a delta function at a particular position and orientation in this lifted space, and then just do SE2 Wasserstein interpolation. And so this is an example that sort of makes sense with the car analogy, where you have like your source and target. When you have isotropic, it's got this skidding like behavior. So where it's pointing to and where it's moving are not in sync. But when you have anisotropy, then you have this turning sort of like behavior that happens from the source to the target. Okay, and finally, we did nonlinear diffusion using a gradient flow for a similar type of an image containing local line structures, right? And one can see that it does indeed have this sort of line completion like behavior where it sort of identifies the main dominant line structures in your image. Okay, so that was all about what the experiments that we had in this paper. And looking ahead, what are some things that I hoping would be exciting to do is sort of use this in, for example, something like tractography. So you have, say, a source and a target region in say, from diffusion weighted MRI, right? And you would want to use some of these metrics and transport to sort of give you an interpolation or a tract between your source and target. So in this simulation here is, this is not SE2, by the way, this is just R2, but with a local metric tensor. So you use your diffusion tensor as an approximation, as a local approximation of your distance, and your transport gives you sort of like a tract from the source to the target. And also something that is interesting would be to build autoencoders which are equivariant in their latent space. And so for most of the results that I show here, we use orientation scores, but it would be nice to sort of learn that representation from data, right? And do, instead of a linear interpolation in your latent space, do a Wasserstein interpolation, and then hope to have like a equivariant sort of representation of your data. Okay, so in conclusion, at the end of the day, optimal transport on homogeneous spaces is equivariant for left invariant metrics. We can generally sort of approximate Lie group kernels and distances well using these logarithmic coordinates. And barycentric interpolation with these anisotropic metrics has these contour concentrating behavior. And it would be very, very interesting to sort of apply this to other Lie groups of interest, for example, say SO3, SE3, and also using some non-trivial metrics, for example, something like a Finsler metric. Yeah, and that's about it.
Let me share the image.
Mm-hmm.
Orientation is the kind of tangential orientation of the shape.
Uh-huh.
It's a great. What is the orientation on an image?
So it is indeed the tangential. So you have these cake wavelets with a particular orientation, and when you convolve, it picks out sort of the orientation that agrees with that. So it does pick out the tangent to the curve of sorts.
And so your metric kind of say how much you're allowed to move tangentially or normally, because for the three figure, it shows the normal orientation, and it's often, and you have
growing
according to the normal, but
right.
It should show the tangential and in favor of this one.
Right. I'm glad you brought that up. That is indeed, in the case of the Eulerian, when I work with orientation scores, I choose the tangential orientation, And for the Lagrangian one, I have chosen the normal one. But yeah, generally speaking, I don't recommend doing this at all. So in most applications, it's beneficial to just work with orientation scores with the tangential. Yeah.
I'm curious about your what you said about autoencoder.
Mm-hmm.
So you say that what? You say the latent space could be
Defined on M2, for example.
yeah, but how you could that makes sense to say that the latent space is LN2, for instance?
So for example, one can think of an orientation score as a particular kind of latent representation of your image, right? And instead of an orientation score, why not just have a neural network just learn that representation from data? So instead of using these cake wavelets with an orientation, one can design, say, a GCNN or a PDE-GCNN that I talked about earlier. Use a network something like this. Like this, these ones, and work with a function on M2. The disadvantage is that you gain a dimension, right? Because you want your M2 is essentially it's 3-dimensional, whereas an image is 2, and so you have to. So it's still, one has to work out how to sort of make your latent representation sparse.
Okay.
Right? But if you do, then you can just work with sort of interpolating between these sort of learned orientation scores and then decode it back. So that is actually what you see here in this visualization here. Is basically that. So it's a GCNN that was trained end to end. So given an image, you lift a couple of GCNN nonlinearities, and then you have one latent representation. Then do a couple of decoding.
No, but yes, but I was thinking that this latent representation is very high level, so it's harder to think that you could put it in some kind of M2 space or something like that, because it's
I see. What I meant is totally like a learned version of the orientation score, which is non-linear. In orientation score is linear, like you just convolve with the cake wavelet, but doing something more sophisticated.
so numerically, what are the ingredients you need? In fact, if you want to extend to SO3, what would be the
so you would need an SO3 group convolution, right? One would need to derive the formulas for the kernels for SO3, the approximation of local geodesic distances in SO3, probably using the same trick that we show here with like logarithmic coordinates, and try to do the same thing over there, right? So I would assume that one can work with spherical images, right? And essentially do the same thing.
I just have a question about the lifting technique at the beginning. So, because you compute wavelet recomposition, so it gives you coefficients in the 3D space, but you can, when you reconstruct the image itself, not the. I missed something somewhere. Like what you reconstruct is the image in R2 cross S1 or in R2?
The reconstruction is in R2.
But you have just a wavelet composition, or you have indeed a full image in R2 cross S1 also? That's what
So I'm not sure if I
think you showed, in your picture, you said you had the image, then you go in 3D space, then you perform your file stuff in 3D space, and then you always project back by summing over theta. So I think all the Wasserstein barycenter interpolation happen in the 3D space.
Absolutely.
But whenever you display stuff, you always integrate.
Absolutely. Absolutely.
But that's not my question. My question is how do you compute the 3D image?
So you choose
Position and orientation.
you choose a filter, say let's say a cake wavelet here, and do a R2 convolution with it.
So this gives you wavelet coefficients.
So this gives you a response of your image for this particular filter, which is parameterized with orientation, right? So if for a particular
Okay, and you take this as the coefficient at this position and orientation.
exactly.
Okay. I thought it would give a wavelet decomposition, and then you would need another process to compute the actual 3D image.
Multi-scale, no, this is just one. Yeah, there is no multi-scale aspect. I mean, just adding up along the
So
theta direction.
it's not the exact. It's a already conversion. There is blurring in the process.
Right. I mean, the designing this cake wavelet will involve certain choices of like how big is your lobe. I mean, so there will be some kind of smoothing that would happen.
Actually, how the wavelet, what is the return of the rating? How you sensitive to the white? I mean, because if we saw the 3 transformed to an 8, we have very different fitness. Is it sensitive to the fitness of the wavelet, or? I'm not sure if you just have to include the wavelet to have a high signal, or if, for example, you have very thin wavelet and a big structure, do you detect?
So this is basically like a line detector, sort of. So a wavelet has like a dominant main lobe with 2 small side lobes, right? And so when you have a perfect match, it sort of gives you a line detection at a particular.
So you have to the thickness of the sign of power.
It is. So this thing, choosing this cake wavelets has parameters to it, basically. Like, so I can choose a different sort of like the way these wavelets are constructed is in the Fourier domain you have a disk, right? And you break this disk into sort of like pies, and then you do inverse Fourier transform of that, and that's what you see here. Does that make sense? So you could.
So you have to deal with structure that have a robust fitness across the process that you want to apply, or?
We choose a particular cake wavelet and work with that. A particular cake wavelet and work.
Did you try several
Filters for
matching and see?
No, I have to say we didn't. I just took a particular cake wavelet and then worked with that.